begin our study of the analysis of circuits with sinusoidal inputs, we're going to analyze the relatively simple circuit shown here. We want to analyze it in what we call the time domain. For now, we can just think of that as the way we would normally analyze a circuit. And what we're going to find is that for a circuit even as simple as this one, we have to do an awful lot of algebra, and it takes a lot of work just to get the answer, such as finding the current through this loop with 3 elements in it. Well, let's proceed with the analysis. To begin, we'll start by using Kirchoff's voltage law to write an equation for the voltage around the loop. Going around the loop, we're going to have the voltage across the inductor, VL, plus the voltage across the resistor, VR, minus the voltage across the source. So we can write then that VL plus VR minus Vm cos omega t all adds to 0, where we recognize that the voltage across the inductor, VL, will be given by L times the derivative of the current with respect to time, and VR, the voltage across the resistor, will be R times the current as a function of time. We can make those 2 substitutions, and that will allow us to write an equation that says L times the derivative of the current with respect to time plus the resistance times the current must be equal to the applied voltage Vm cos omega t. Probably recognize this as a differential equation, and we can solve it in a variety of ways. What we're going to do here, to focus on finding a solution and not focus on differential equations, is to assume a solution of the form I of t will be equal to some constant a times the cosine of omega t plus b times the sine of omega t. Why do we assume a sine and a cosine when we only have a cosine in the function? Well, we know we're going to take a derivative somewhere along the way, and the derivative of cos is minus sine, so we might as well prepare for that at the outset. You'll notice that we also are going to need the derivative of this function with respect to time when we go to substitute it back in, and that derivative is minus omega a times the sine of omega t plus omega b times the cosine of omega t. We can now substitute those terms back into the equation, and that's going to lead to this rather large equation where we'll have omega L times A sine omega t with a minus sign plus omega L B cosine omega t plus R times A cosine of omega t plus R times B sine omega t, all equals our applied voltage Vm cosine omega t. We can now solve for our constants by equating coefficients. For the sine terms, we can see that we'll have minus omega LA and we'll have RB, or we can say that RB will be equal to omega L times A. We could solve for B if we want and write that as omega L over R times A. On the other hand, for the cosine terms, you can see that we're going to have omega L times B plus R times A, all equals Vm. Well, I can substitute for B already, we know what that is, so I can rewrite this as, now I'll have omega squared L squared over R plus R squared all times A should be equal to Vm, and that allows us to solve for A, and we find that A will be equal to R over R squared plus omega squared L squared times Vm. Knowing A, we can also find B. B will be then equal to omega L over r squared plus omega squared L squared times Vm. With those two factors, we can now substitute them back into our original equation and write that our current as a function of time is equal to, I won't use the word simply here because it's definitely anything but simple. Substituting for A, I'll have r over r squared plus omega squared L squared cosine omega t plus b sine, where b is omega L. Forgot the Vm back here. See how non-trivial this is. Omega L Vm over r squared plus omega squared L squared times the sine of omega t. Well, that looks rather unwieldy, but you might recall from trigonometry that if I have a cos x plus b sine x, I can reduce it down to a function of only cosine by taking the square root of a squared plus b squared cosine of rx minus tan to the minus 1, or the inverse tan of b over a. If I go ahead and use that alternative form, I can rewrite my current equation to be strictly a function of cosine instead, and now I can write I of t will be equal to Vm, the amplitude of the voltage, divided by the square root of r squared plus omega squared L squared times the cosine of the frequency omega t minus the inverse tan to the minus 1 of omega L over r, and that becomes the current that flows in the circuit that we're analyzing. Rather an unwieldy equation, but we can make some observations. Aside from the obvious observation that was rather a lot of work, and we really would not want to ever have to do this again, and hopefully we won't. But the observations that we can make is, first of all, the amplitude is changed. The amplitude in was simply Vm, and the current out is going to be a scaled version of that. The second observation we can make is that the phase changes. Our input was a cosine, and our output is also a cosine with a phase shift, so we can say that the phase has changed as well. The third interesting point to note is that our input frequency was omega, our radian frequency was omega, and the frequency of the output is the same. This last point is very important, and it's indicative of a linear circuit. A linear circuit is a circuit in which if we drive it with a sine wave, all the voltages and currents in that circuit will be a sine wave at the same frequency. They'll have different amplitudes and different phases, but the frequency will be the same. We will go on and see how we can use this in the following videos.